Electricity powers everything around us: homes, hospitals, transportation, industry. Yet for more than a century, the power grid was never designed to defend itself from cyber attacks. Not because engineers were careless, but because for a very long time there was simply nothing to hack. So how did one of the most reliable engineering systems ever built become a cyber target? To answer that question, we need to go back. Long before hackers, computers, and even the internet existed. This is the beginning of the story of cyber attacks on power grids. For most of its history, the electric power grid was a purely physical system. Early power systems were built from generators, transformers, transmission lines, relays, and circuit breakers. Everything was governed by physics, mechanics, and electromagnetism, not by software. There were no digital controllers, no communication networks, no remote access, no centralized control rooms filled with screens and servers. In simple terms, the grid was isolated. It wasn't secure by design, it was secure by the absence of connectivity. If you wanted to disrupt electricity, you had to be physically present. You had to cut a line, damage equipment, or sabotage a substation. From a cyber perspective, the grid simply did not exist. The story begins in the late 19th century. In 1882, Thomas Edison commissioned the Pearl Street Station in New York City. It was the world's first commercial electric power distribution system, supplying direct current, DC, to nearby customers. This system was small, local, and completely mechanical. A few years later, during the famous War of Currents, Nikola Tesla and George Westinghouse introduced alternating current, AC, systems. AC made it possible to transmit electricity over long distances using transformers. This single innovation allowed power systems to expand rapidly across cities, regions, and eventually entire countries. But despite this rapid expansion, one thing remained constant. There was no digital control. In the early decades of power systems, protection and control were entirely local. Each substation operated almost like an independent island. Protection systems were based on electromechanical relays, devices with coils, springs, rotating discs, and mechanical contacts. They measured current and voltage, and when something abnormal happened, they acted instantly, without asking permission from anywhere else. There were no digital devices, no data networks, no remote monitoring, no centralized control centers. Decisions were made locally, automatically, and physically. From a modern cybersecurity viewpoint, these systems were untouchable. You couldn't hack a relay made of copper coils and steel springs. Between 1930 and 1980, power grids grew massively. National transmission networks were formed. Interconnections between regions increased. Reliability became a top engineering priority. Yet the control philosophy barely changed. Protection logic was fixed in hardware. Relays worked independently. Communication between substations was minimal. Even when telecommunication lines appeared, they were mainly used for voice communication or very simple signaling, not data exchange. During this era, the grid was powerful, reliable, and silent, and most importantly, it had no cyber attack surface. The only real threats were physical sabotage, natural disasters, equipment failures, human error. Cyber attacks were simply not part of the conversation. Everything changed in the late 1980s and 1990s. Electromechanical relays began to disappear. They were replaced by static relays and later by digital or numerical protection relays. These new devices brought major advantages: higher accuracy, faster fault detection, flexible protection settings, event recording, and fault analysis. But they also introduced something entirely new into power systems: software. For the first time, protection decisions depended not only on physics, but on code. Digital protection alone was not enough. To fully benefit from these new technologies, utilities began deploying communication networks. Fiber optic links connected substations. Pilot protection schemes exchanged data in real time. SCADA systems enabled remote monitoring and control. RTUs collected field data and sent it to control centers. Substations were no longer isolated islands. They became nodes in a network. This connectivity dramatically improved efficiency, visibility, and control, but it also changed the threat landscape forever. To allow devices from different manufacturers to communicate, standardized protocols were introduced. Protocols such as IEC 6N870 CUFA5, DNP3, Modbus later, IEC 61850, revolutionized substation automation. It introduced Ethernet-based communication, station buses, process buses, and real-time data sharing between intelligent electronic devices. At this moment, the power grid crossed a critical threshold. It became a cyber-physical system. Here is a crucial point that is often misunderstood. Cyber attacks on power grids did not emerge because hackers suddenly became smarter. They emerged because power grids became connected. Once substations, control centers, and protection devices were linked through communication networks, and sometimes indirectly connected to corporate IT systems, the grid became exposed. Cyber attacks are different from traditional failures. They are invisible. They are fast, they can be launched remotely, and they can bypass physical protection entirely. Traditional power grids were safe by isolation. Modern power grids must be safe by design. This requires cybersecurity awareness among power engineers, clear separation between IT and OT systems, security standards and regulations, continuous monitoring, and risk assessment. The goal is not to reverse technological progress, but to secure it intelligently. This video marks the beginning of the story. In the next episode, we will explore what happened when power grids truly went online, and how real cyber attacks changed the industry forever.